In section 7.4, we're going to talk about Euler equations. So if we recall from our series solutions in 7.2 and 7.3, if we consider the homogeneous equation where we have a function of x in front of the first derivative, another function of x in front of the first derivative, and a third function of x in front of y, we know that our solutions can occur near P of x naught. Also, I want you to recall that a point x naught such that P of x naught equals 0 is singular. We call that a singular point. The simplest kind of equation with a regular singular point at x naught equals 0 is the Euler equation. So what does the Euler equation look like? An Euler equation is an equation that can be written in the form ax squared y double prime plus bx y prime plus c y equals 0, where a, b, and c are all real constants such that a does not equal 0. Notice that it resembles a quadratic in x mixed in with a second order differential equation. We're going to be focusing on solutions only for positive real numbers. So for x greater than 0, x to the power of r is going to be defined as a real valued function on 0 to infinity for all values of r. So this is very similar to what we were doing in section 5.2 when we were letting y equal e to the rx. It was an exponential with a power of rx and a base of e. Instead, we're going to be looking at a different type of function here, but now we still have a base of x and an exponent of r. It's going to be a similar process to exactly what we learned in section 5.2. So if we substitute y equals x to the r into our given Euler equation, we find that we get ax squared times x to the r double prime plus bx times x to the r prime plus cx to the r. If we take those derivatives, we end up with ax squared still times the second derivative of x to the r would be r times r minus 1 times x to the r minus 2 plus bx times the derivative of x to the r, first derivative, and that would be r x to the r minus 1, and then plus c times x to the r. If we factor out an x to the r from all of those terms, we find out that what we're left with on the inside is ax squared times r minus 1 times x to the minus 2, because we have the r and the minus 2. That's the same as x to the r times x to the negative 2, right? So x to the r minus 2 is the same as x to the r times x to the minus 2. And we just factored out the x to the r. Same thing if we have x to the r minus 1, that's the same as x to the r times x to the minus 1. And we find out that both of those come up within our simplified version of the equation. But once we start combining exponents of the x's that are inside the parentheses, we find out that after we factor out this x sub r here, we're left with ar times r minus 1 plus br plus c. And this form, if you'll notice once more, is another quadratic. And much like the different forms of solutions we had in section 5.2 based on the solutions of our quadratics in terms of r, in that case, we have different kinds of solutions for Euler equations, also based on the types of values we get for r in our Euler equation. So if we look at our polynomial, the indicial polynomial, P of r, that equals AR times r minus 1 plus BR plus C. So we call that our indicial polynomial, and when we set it equal to 0, we have an indicial equation. Much like when we solve the y equals e to the rx, we have a characteristic equation. And again, much like when we sought solutions of the form y equals e to the rx in chapter 5, here we're seeking solutions of the form y equals x to the r. So if the indicial equation has distinct roots, then we have y1 equals x to the r1 and y2 equals x to the r2. which again is very similar to we had y1 was e to the r1x, and we had y2 was e to the r2x in chapter 5. And they form a fundamental set of solutions on 0 to infinity, and their general solution then would look like c1x to the r1 plus c2x to the r2. Again, very similar to c1 e to the r1x plus c2 e to the r2x. There are a lot of parallels with this section and section 5.2. So again, analogous to section 5.2, we have a theorem that provides formulas to solutions for Euler equations with repeated roots and complex conjugate roots. And there are proofs in the text, but we won't have time necessarily to go through those together. So if we suppose the roots of the indicial equation are R1 and R2, then if R1 and R2 are distinct, which is what we were just discussing, if they're distinct, then we have C1 x to the R1 plus C2 x to the R2. If R1 and R2 are the same, then our solution is x to the R times C1 plus C2 natural log of x. So while this is analogous to section 5.2, the solutions do not have the same form. And likewise, if we have complex solutions, and in this case we have them as lambda plus or minus I omega, then we have solutions of the form x to the lambda times the quantity C1 cosine of omega natural log x plus C2 sine of omega natural log x. We're going to go through problems of each type together. So let's look at an example. We have 6x squared y double prime plus 5x y prime minus y equals 0. And remember, our indicial equation is AR times the quantity r minus 1 plus BR plus C equals 0. And in this case, A is 6, E is 5, and C is negative 1. So we have A equals 6, B equal 5, and C equal negative 1. So if we plug those in, we end up with 6r times r minus 1 plus 5r minus 1 equals 0, or 6r squared minus 6r plus 5r and minus 1, or 6r squared minus r minus 1 equals 0. So I like to do factoring by grouping using the AC method. So the way I see this is what multiplies to give me negative 6, adds to give me negative 1. So that would be negative 3 and positive 2. So I break that middle term up into negative 3r and a plus of 2r. So when I factor out a 3r from the first two, I get 2r minus 1 plus, I only need to take out a 1, 2r minus 1. So we end up with 3r plus 1 times 2r minus 1 equals 0, or r1 equals negative 1/3, and r2 equals positive 1/2. In this case, we have two distinct roots, so we can say then, okay, that means that y of x is equal to c1 x to the negative 1/3 plus c2 x to the positive 1/2. And that's our solution. In section 5.2, in class, I walked you through using variation of parameters to find a second solution when we had a repeated root, so that we didn't have two linearly dependent solutions to our second order constant coefficient problem when it had the same roots to the characteristic equation. In the same way, I'm going to walk through here using reduction of order to show why the general solution in this case for our Euler equation looks the way it does. Because this one isn't as straightforward as, oh, just multiply the second one by an x. Now it involves things like a natural log of x. So let's see how that comes about. So we know that our indicial equation, AR times r minus 1 plus BR plus C equals 0 comes into play here. So we also know that we have A is 1, B is -5, and C is 9. So we really have R squared minus R minus 5R and plus 9 equals 0. Or R squared minus 6R plus 9 equals 0, or R minus 3 quantity squared equals 0. So R1 equals R2 equals 3 here. So we know then that Y1 is going to be x cubed. If we use reduction of order, so we're going to use reduction of order to find R2, or sorry, Y2. Let's see what happens. We end up with Y2 equaling Vx cubed, which means that Y2 prime would be V prime x cubed plus 3x squared V. And Y2 double prime would be V double prime times x cubed plus 6x squared V prime plus 6xV. And I'll let you work out the product rule and combining like terms to make sure that you agree with that. So if we plug it into our equation, we end up with x squared times V double prime x cubed plus 6x squared V prime plus 6xV minus 5x times the quantity V prime x cubed plus 3x squared V plus 9 times y, which is x cubed, and it all equals 0. Oh, I forgot my V. Sorry about that. Let's include that V. 9 Vx cubed. There we go. Can't forget the V. So when we multiply things through, we get V double prime times x to the 5th plus 6x to the 4th V prime plus 6x cubed V minus 5x to the 4th V prime minus 15 x cubed V and plus 9x cubed V. So if we were to look at the different kinds of terms we have a 6 to the 4th V prime minus a 5 to the 4th V prime. So we already know that we're going to have an x to the 5th V double prime, plus now we just have one x to the 4th V prime left. And this is where our dummy check comes in. We should have it that all of our x cubed V terms cancel out. Well, if I have 6, let's see here, there we go. If I have 6 x cubed V and I add 9, that's 15, and then I take 15 away, so our dummy check holds. We definitely did something right because now this just equals 0. And then we know we let W equal V prime and W prime equal V double prime. So when we plug it in, we get x to the 5th W prime plus x to the 4th W equals 0. And again, here you can use a linear integrating factor or you can use separation of variables. I tend to use linear integrating factor. So first things first, we have to divide through by x to the 5th. So we get W prime plus 1 over x W equals 0. So in this case, our mu of x here is going to be e to the integral of 1 over x dx, or e to the natural log of the absolute value of x, which is just x. So we end up with x W prime plus W equals 0, or x W quantity prime equals 0. So we end up with x W equals C1. And that means W equals C over X. We also know that W is the same as V prime, so that means V then is the integral of c over x, or in fact, this should be c1, sorry. And we know then that that would be c1 times the natural log of x plus c2. So what we end up with then is when we say then y2 equals vx cubed, we end up with y2 is c1 x cubed natural log of the absolute value of x plus c2 x cubed. Well, and again, this is where we let c2 be 0, right? Let this go to 0 because this is y1. And we'll let c1 go to 1. So we really end up with y2 being x cubed times the natural log of x. Natural log of the absolute value of x. So in this case then, our full solution would be, our general solution here would be that y of x is c1y1 plus c2y2 would be c1 x cubed plus c2 y2 is x cubed natural log of x. And that is our solution here. So this is where that natural log of x comes from in the formula that's given by the theorem. You do not have to go through reduction of order here to find y2. You can just use the formula given in the theorem. Much like in section 5.2, you didn't have to go through variation of parameters every time we had a repeated root to show that the second solution would have an x multiplied. Same thing here. Just use the formula and the theorem from here on out, but I wanted to show you why it works that way. For our third and final example of the different types of Euler equations we can have based on the indicial roots, we have another one where we're going to have complex roots to the indicial equation. So remember, we have AR times R minus 1 plus BR plus C equals 0. In this case, A is 1, B is 3, and C is 2. So we end up with R squared minus R plus 3R plus 2 equals 0. Or R squared plus 2R plus 2 equals 0. This yields an R that is equal to -1 plus or minus I. I'll leave you to do the quadratic formula for yourself on that one. So when we plug it back in, we end up finding out that we have y1 equaling x to the -1 plus I, and y2 is going to equal x to the -1 minus I. Or, well, we can't really use Euler's equation here that we use, or Euler's formula, I should say, that we used when it was e to the alpha plus or minus beta t. What we can do, though, is we can make a substitution. We said, but what if I want to use Euler's formula? Can I do that? And the answer is yes. The question is, how am I going to do that? We're going to make a substitution. So we're going to say, okay, let's let x equal e to the t. Because then I now get y1 is equal to e to the -1 plus it, and y2 then is e to the -1 minus it. We now know how, we know exactly how, right? To transform these into sines and cosines. So that tells us, oh, well, in this case, we get y equaling e to the -t times c1 cosine t plus c2 sine t. We know how to do that, but we still don't have this back in terms of x. What else we need to do is if we so we had x equals e to the t, we can solve for t in terms of x. So solve for t by taking the natural log of both sides. And then what we're going to say is, okay, well, that means now I can retransform or rewrite this to transform it back into a function of x's. Well, I no longer have a t, so it's now e to the negative natural log of x times c1 cosine of natural log of x plus c2 sine natural log of x. And this agrees with the formula we were given because here omega is 1. For homework, I gave you one of each type of problem with each type of root, and you can just use the theorem that was provided in this section. So you're only looking at problems 6, 9, and 10.